What's been going here this morning? All right. How you guys doing?
Pretty tired.
Yeah.
Dog keep wanting to wake up at 5:30 in the morning.
Yeah.
I'm at like 6:30 in the morning, so I'm doing all right.
In that extra hour of sleep, right?
Yeah.
See, she sees that sunrise and starts barking like crazy.
Put a towel over her.
That's what I'm gonna start doing. Yeah.
100% put a towel.
But no, dude, she's getting big. She just hit 10 weeks. Take her in for her round of shots tomorrow. My guess is she'll weigh in around 18, 20 pounds.
I believe it. Mine's up to about 25, 26 probably.
She's gonna be big.
All right, guys. Since we're talking about dogs, let's talk about quirks.
What's that have to do with dogs, Dr. P?
They're both a pain. As comforting as they are on cold winter nights, nothing like a good quirk. All right. We need to talk about field theory a little bit. So we studied the harmonic oscillator, and we used Schrodinger's equation to get a quantum mechanical view of the energies and the wave functions of a harmonic oscillator. And we treat free electrons interacting with an electromagnetic field like oscillators, and that works pretty well. But here's the quantum field theory point of view, is that we're treating the electromagnetic waves classically, and we're treating the harmonic oscillator quantum mechanically. And we really need to treat them both quantum mechanically. And so it ends up that the harmonic oscillator is a good model for the electromagnetic field. And that is, the field is a source of photons that are all just sitting and oscillating. And mathematically, some of you discovered in the harmonic oscillator problem, some of you didn't, that there's a much quicker way algebraically to solve the problem than doing differential equations. And that's creating something called a raising and lowering operator. And what that does is it takes one unit of energy away from the harmonic oscillator, or gives one unit of energy back to it. And so we look at the electromagnetic field as a whole bunch of different harmonic oscillators, one for each natural frequency. And that when a particle interacts with an electromagnetic field, that it either absorbs or gives one photon using this raising and lowering operator. So that means we can describe now an atom, for instance, quantum mechanically, in an electromagnetic field, quantum mechanically. And they interact with each other by exchanging photons, which is the exchange particle of the field. We've taken that idea and applied it to every field, that every field has at least one exchange particle, and that you've got other particles interacting with that field with those exchange particles. So the first attempt at that was looking at how a neutron and a proton interact. And that's this drawing here. And this kind of drawing is called a Feynman drawing. And there's nothing consistent between these drawings up on the top and the bottom, because the arrows usually point in the direction of time. So over here, time is going up. Over here, time is going up. The Feynman diagrams in your textbook, the time is going down. Down here in this bottom one, the time is going to the right, which is the preferred way of doing Feynman diagrams, but only by about 35% of the people. The other 65% split between going up and going down. So you always have to be careful to watch the direction, the general direction of time. Now, particles can move backwards in time. That makes them antiparticles. This is something you'll discover from Feynman diagrams. And we're going to spend today and Wednesday doing Feynman diagrams to finish out our study of the Standard Model. So this particle here, the exchange particle, is a virtual particle. It's emitted by the neutron, and the neutron's mass will decrease, and a proton will appear, and a proton will absorb it, and a neutron will appear. Now you might think, well, that's good conservation of mass energy, and that's fine, but the fact that this particle can exist violates all kinds of principles, such as Heisenberg's uncertainty principle. Well, actually, we use the uncertainty principle to justify it. We say that even though it can't exist, it can exist for a short time if its energy is not too big. So there's that Heisenberg uncertainty principle of the uncertainty in the position times the uncertainty in the momentum is greater than or equal to h bar over 2, I think. And if you did the harmonic oscillator problem, you found that h bar over 2 idea isn't an exact idea. It's just that that's sort of a minimum that we can come up with. In fact, for some, that uncertainty is h bar over 3 or 3 h bar over 2 or 10 h bar over 2. So there's a complementary uncertainty principle that Einstein came up with, even though he didn't like the idea. He pointed out that it must exist if the first one does, and that is the uncertainty in the mass energy of a particle times the uncertainty in the mass energy of uncertainty in the time must also be greater than h bar over 2. So the uncertainty in the mass energy right here of this neutron giving up the proton and turning itself into a proton and a pi meson can happen for a very short period of time. And that period of time is what really dictates how far away particles have to be to interact with the strong force. And it ends up being about 1 femtometer. With the discovery that neutrons and protons are made up of particles, and the idea came, and that the pi meson itself is made up of other particles, those particles being quarks, then the question is, are we really exchanging a pi meson or are we exchanging quarks? And so here is the same event, a neutron and a proton coming in. Here's the neutron and the proton coming in, and a proton and a neutron going out, a proton and a neutron going out. And here then is the exchange. That what we had called the pi meson is now a mess of other things. And it ends up that the gluon is a kind of a carrier of quarks. And so a d quark here, looking backwards, we would have, so this is, I'm going to turn time around on you. When you look backwards, this would look like an anti-D, but this is still going the other direction, so it's a D. So it looks like the quark looks like something like a D anti-D. So it kind of looks like it's got two quarks in it. So if I emit a d quark here, where did that d quark come from? And I needed to have an anti-d go with the g in order to allow the d to be created. And the g carries not just the anti-d, but another quark, a u quark. And then at the same time, this particle, the u, is creating an anti-u, and so it has to carry a u with it and carry also the d. So you get this funny business of this quark that is emitted with it's this particle, the gluon, it's called, seems to carry two quarks, one associated with the quark that appeared, and one associated with the quark that appeared later. And this is the process for this formation. So this is how we're dealing with Feynman diagrams. And then with the with the gluons and the quarks came the understanding that that we had to create a new quantum number called color. And the quantum number was going to have three versions called red, green, and blue. And from that, we discovered that the quark also carries color, a color and its anticolor. So we don't even show the anticolors here. And it's the interaction between red and anti-red that is the nuclear force, or green and anti-green, or blue and anti-blue. It ends up that reds and reds repulse each other, greens and greens repel each other, blues and blues repel each other. Reds and greens and blue weakly attract each other, but reds and anti-reds very strongly attract each other. Blues and anti-blues strongly attract each other, and so on. So we look at the gluons not so much as what kind of quarks we're looking at, but their colors. And so if we've got red, green, and blue, and anti-red, anti-green, and anti-blue, how many different quarks can we have? And here's the requirement. You have to carry a color and its anticolor, and an anticolor, not necessarily just red and anti-red. So, how many can you think of? Well, the answer is going to be 8, and you can puzzle over that one for a while. But it's the Feynman diagrams that I wanted to look at a little bit today. Your book does a terrible job with this presentation. And so we're going to have to go over to the whiteboard for this for a little while. So let me make that disappear. So if I had two electrons, that are coming along and colliding, and if they go off like so, that's a classical way of describing things. A more quantum mechanical way of describing them would be to consider the incoming electron as a plane wave with a de Broglie wavelength, and it enters a scattering position here, which scatters out like water waves on the lake hitting a stone and producing waves that go out like this, and another particle scattered out. And these would condense into being in whatever direction the other electron took. That would be more of a quantum mechanical way of describing them with wave functions. But a better way, and I'm going to have my Feynman diagram with the time going to the right, is to have two electrons interact with each other by exchanging a photon. And that's the field theory way, and this is called a Feynman diagram. And so I would show this process here.
So from classical point of view, they like touch each other and exchange quarks?
This is a photon right here.
Yeah, I'm asking about the
classical, they don't have to touch each other. You're dealing with the classical electromagnetic field. So they would get close to each other, just like when the satellite that we've launched that's supposed to go and orbit Mercury in near the sun, we launched it, sent it out to Mars, had it scatter from Mars, come back, and last week or week before last, it scattered from Earth to slow it down enough that I think it's got to undergo 2 or 3 more of these scatterings so that we can slow its speed down enough so that it will take up an orbit and interact with Mercury. And when it gets into that orbit, they will fire retro rockets to slow it down more so it can get captured by Mercury. And we can take pictures of Mercury's surface. None of those scattering events involve the satellite colliding with Mars or Venus or the Earth. But in each case, the satellite came in and interacted with the Earth and scattered. And the Earth was, to conserve momentum, had to scatter backwards, but not by much because we're a whole lot more massive than that satellite. Now, it's possible that you can get something that will collide head on. That's how we have all the craters on the moon. But they can also scatter and miss. So classically, they don't have to touch, but they can. That's another event. So this is what we're going to look at, these Feynman diagrams. So I'm going to start you off with a couple out of a textbook here, and you're gonna get all this or some of this material sent to you this evening. I'm going to have let's see. I'm sorry, this is a pi meson plus a proton. Go to a pi 0 and a delta double plus. Now, if you've got your book open, we need the quark makeup of these. And I think this is page 575. Of course, your book's incomplete there too, so I'll have to help you out. The delta plus plus is a U particle. Okay, so here's what I've got. I've got a pi plus. What's a pi plus according to your textbook, quark-wise?
U anti-D.
U anti-D. All right. And the proton is a DUU particle. Okay, so particles go to the right in time, antiparticles go back in time. So I can look at this as a rearrangement of quarks. Up here, so I've got a U here. Up here, I've got an anti-D and a D. What's an anti-D and a D?
Pi 0.
Right, it's a meson because it's got two quarks, and if you look up, they do have a complete table of the, almost complete table of the mesons. Okay, so there's a simple one. We haven't included all the effects though, because we're not showing, really, you don't rearrange the quarks, you use gluons to do that. So we've got more to learn in this process, but we need to get used to the Feynman diagrams right now. So let me throw up one here and see if you can tell me what this is. What do you think that is?
Electron and photon.
It is, but what's happening? Right up here at the top, something came in and something went out. So here's what came in, and here's what came out.
I mean,
So
this
what
stuff's
came in
still
over here?
going out, isn't it?
Is it a de-excitation of an electron?
So would this be a proper way of saying that's what came in?
Yeah.
What's going out?
Same thing.
Same thing. What process is that?
It's like absorption and remitting.
Or Compton scattering?
Why do you need arrows on the photons?
They
Like-
never do. They never do.
Okay.
Okay, so now I'm going to give you another one here. What is this?
Is it a pair or like electron positron annihilation?
Yeah, so it's so it's E plus E minus goes to 2 gammas.
Let's go.
Oh, let's go, baby.
So what kind of particle electron and the positron?
I missed some of that. Your microphone killed you.
Yeah, sorry, I was asking. Yeah, what kind of exchange particle?
Oh, that's a good question. So this is an exchange particle of some kind right here. And we're not quite ready for that yet, but I'll get you there. All right. So let's try one of the collisions we were looking at last time. See, E minus. We were looking at this event. Where this was actually a D plus.
Dr. P, I just have a quick question.
Yeah,
On the last diagram for the electron positron annihilation, you had the arrow, like the electron. Oh, sweet, you still have that. Why is the arrow going up on the positron? As if it's
Okay,
going
so
away from the interaction.
time is going this way.
Okay.
So these two particles are actually coming together. But remember, the arrow on an antiparticle goes backwards.
Okay. Gotcha.
All right. How do we handle something like this? An electron doesn't have a quark structure, does it?
No, but it's
But it still has to come
fundamental
in.
particle by itself.
So I'll bet you the electron does something like this. And we're going to have a proton coming in, aren't we? So now what happens? Yes.
Wait, why did the electron, was it attracted to the proton and then repelled away from it?
It's a collision.
Okay, so that's where they hit. So why is there not there's no gluon because there's no structure in the electron?
There's no structure to the electron. So it's bringing in energy and momentum is what it's doing.
Okay.
So here's the rule about Feynman diagrams. You can't have, you can't have this kind of structure. You can only have 3. So what do we do?
So what was wrong with this kind of structure?
There were 4 prongs to it. You can only have 3.
All right. Something like we find from experience, or it's just the theory?
It's the. By the way, there's this. Each of these drawings is represents a rather complex integral, and you have to have 3 prongs at any intersection point. Okay, so let me go back a second to this one. So we had, you notice we had to put this here. You didn't question that. We couldn't have a gamma coming in, a gamma coming out, an E coming in, an E coming out. There has to be something there. Same thing here. Yeah. So this is kind of how you would do it. Now, can you put the quarks in? Or before we do that, maybe we should finish up this part of it here. So I have this, and it looks like we would like to say this becomes a pi plus and a neutron. Now, is the pi plus a particle or an antiparticle?
Antiparticle. Particle because of the arrow.
I put the arrow on there.
But you're wrong.
I'm saying I might be wrong. That's why I asked. So the pi plus is not an antiparticle. So I got the direction right. And the neutron is not an antiparticle here either. So, how do we fill in the quarks?
We guess.
You don't have to guess. All these particles have known quarks. Yes, no?
They do.
What's the proton made up of?
UUD.
UUD. What's the delta plus made up of?
I'm not seeing it on this chart.
They didn't put it on there. Let me see if I can find it in here.
It's
There's like-
UDU.
The delta plus is a UUD. Is that right?
Yeah, that's right.
Cool. So this one's not so hard, is it? We have the UUD coming in and a UUD going out. So let's look at the UUD going out. What's a neutron?
Neutron's UDD.
UDD. And what's the pi plus?
The pi plus is U anti-D.
So, what's taking place here with the quarks? Looks like we've got one quark going here, one quark going here, and then what's this one doing? Got any suggestions?
My suggestion is that the U goes to the other U.
Yeah, I agree.
Or it splits into a U and an anti-D.
Now what do I need? I need an event that will create A quark and an antiquark. All right. So this is the process in these particle creation, is that you create quark-antiquark pairs, which conserves just about everything, since a particle and its antiparticle have opposite quantum numbers. When you add them together, it's as if you didn't change anything. But in that process, we can create these kinds of particles. All right. So we need some sort of exchange particle that gets created that can do these kinds of things. We need something over here that will do this kind of thing. So a U quark and a D quark involve a W plus exchange particle. That's a boson. So this is a U and this is a D. A D can go to a U with a W plus a charm quark can go to a strange quark with a W minus, and a strange quark can go to a charm quark with a W minus.
So these reactions happen like both ways.
Pardon?
You can-
Say that again. You're cutting out on me, so.
Sorry. Yeah. Yeah, does this, like, if this reactions happen both ways?
Time is always going this way.
I mean, so if, I see. But I mean, doesn't this mean like just turn to a D and then the D would just return back to you as long as you have enough energy?
Yeah, your microphone cuts out. I can only hear a few words on it, Allow.
Type
I'm do you hear me now?
Yeah, it's like it's cutting in and out for me too.
Yeah.
Yeah.
So the W exchange particle is a what was called a weak interaction. And that's try typing in there so we can see it. So it doesn't matter if it's a U or a D coming in, the emission of a W plus I should have this, or the absorption of a W plus. I think that was your question. So if a U decays, it will decay into a W plus and a D. If a D comes in, it can absorb a W plus and become a U. If the C comes in, it can decay to a strange quark and emit a W minus. And a strange quark coming in can absorb a W minus and become a charmed quark.
Dr. P, you said a W plus is called a boson, right? Or is it just a boson, right?
It's a boson, right? It's an exchange particle.
So is a W minus an anti-boson? Or is that just ridiculous?
Say that again.
Is a W minus an anti-boson? Or is
I don't think they never refer to them that way, but it kind of acts like it to me.
Okay.
So a pi minus is unstable, and it will decay to a neutrino and an antineutrino and a mu minus. So I'm going to turn this on its side. So what is a pi minus?
Anti-UD.
So that will be going this way and this way. What particle goes here?
What was that, Hank?
All right, so if we turn this on its side, so time is going, well, we don't worry about time. So here's my D, and here's my U bar. If this were a U and a D, this would be a W plus, wouldn't it? That's over here. But, and let's see, this would be, that would be this. How do I get this from this? Where this is a W minus going in that direction. So there's a rule for these kinds of things. And what I'll be sending you are the rules for how you rotate these things, what looks like in time, and how you can take these four and create a whole bunch of other permutations. And it will help us here for this decay process that will produce the W minus, and it ends up that there are the W minus can turn itself into a neutrino and its associated particle of mu, or an electron and an electron neutrino, or a tau and a tau neutrino. So this is how we can completely get rid of quarks and turn them into leptons, is through this W particle, which is a weak interaction. So I'll send you the set of rules, and you can try them out, and then we'll go over several of them next time to get an idea of how this takes place. And when you are studying probabilities for, say, a pi meson decaying, probability per time, which gives you its half-life, this process is one integral. And then any other collection of paths, however Byzantine it may be, that this doesn't turn itself into the W minus to begin with, it turns itself through some gluon interactions into something else. You can get an infinite number of integrals, but the number of steps involved. So here there's one step and then two steps. Determine it's sort of the order of magnitude of the integrals. So if I came up with something with 5 steps, it's probably 1,000 times less likely than this, possibly 1,000 times less likely. And so to do these calculations, you have to be able to write out all the different Feynman diagrams and then do every integral associated with them. So we don't do the integrals. When you take your first field theory course, they'll take a couple of weeks off and you'll learn to do one integral. And then they'll assume that if you can do one, you can do any of them. And
Field theory.
It's field theory. But it's the same kind of idea as an atom absorbing or emitting a photon from the electromagnetic field. The electromagnetic field is a bunch of harmonic oscillators, and the interaction is a raising and lowering operator. And you haven't seen those integrals either, but those kind of interactions involve integrals. So you're just getting a sample of where this stuff goes, and it's really fascinating. And although the integrals are awful to do, they're just awful to do. It's just mathematics. But the ideas behind it are really neat. All right, guys, I've gone way over my time. I'm sorry. I'll send this out to you, read up a little bit on it, and then we'll play our games with these Feynman diagrams again.
Are we going to have a party for the last day of class?
That's doing the Feynman diagrams. What do you mean?
All right, bet. Sounds good.
All right, guys. See y'all later.
Yeah, thank you.
Bye. Bye.
Bye.